Like all my classes with fries.
All right. Good morning, everybody. Welcome back. So let's start today with some important announcements for this coming week. All right. Announcement number one, that don't forget that you have online homework chapter 3 part 1 due on next Monday. So don't leave for the last minute. And announcement number two is that for this week, we will not have in-class assignment this coming Thursday. Okay, so we will not have it. So let's try to regroup, breathe a little bit, and then have the assignment next week, not this week. Okay, so let's start with the lecture. So that was the part that we stopped on Thursday, and that's where we will pick it up. So let me change my screen. Okay, so here is the part where we left last week. So now remember that we are talking about reactions in solution. So now let's start to talk about concentration and dilution. Okay, how to measure the amount of entities in a solution. So let's start that with how to measure the amount of people in a determined volume or area. So if I show you these two pictures, clearly the one on the left side has more people in the same area, and the one on the right side has less people in the same area. So we can say that the figure or the picture on the left side, the concentration of people is higher than the one on the right side. The same idea will work for chemical compounds dissolved in solution. So concentration is a measurement of the amount of entities in a given solution. And here I would like to add two terms. The first one is called solute. Solute or solute is whatever chemical compound in solution. So that can be a salt, an acid, base, oxide, doesn't matter. Is what you are going to dissolve in solution. And then the second term is solvent. Solvent is any chemical compound used to dissolve the solid. Okay? Okay. So I told you that concentration is basically the amount of substance in a given volume. The unit of concentration in the international system is mole per liter, also called molar concentration. And some people like to use the symbol uppercase M instead mole per liter. They mean the same thing. And the molar concentration is calculated as a ratio between the number of moles by the volume. So if we look here at the equation, C means molar concentration, or also called molarity. The units are going to be always mole per liter, okay? Or you can represent mole per liter as an uppercase M. N in the equation is number of moles. The unit for number of moles is always mole. And V stands for volume. Every time that we are talking about molar concentration or molarity, the volume has to be in liters, okay? This is a requirement. Molarity is not the only way to represent the concentration of a solution. Other ways to represent the concentration is also using other units such as kilograms per liter or grams per milliliter. And then we just represent that as a concentration. And here it can be kilograms per liter, for example. So it's going to be always mass over volume. Therefore, M stands for mass and V stands for volume. What are the units that are going to be used? Always look at the units for the concentration. If the concentration is being asked in kilograms per liter, then mass is going to go in kilograms and volume is going to show up in liters. So the problem in this case will specify to you what's the unit for concentration that's being used. And from there, you adjust the mass and volume units, okay? Okay, so at this point, I showed you two ways to determine the concentration. The first one I showed you is called molar concentration or molarity, and that's the official way to represent concentration. Units mole per liter or molar, and it's always the ratio between number of moles divided by volume. Pay attention here because the volume has to be in liters all the time. The second way to represent concentration is more unusual way. and it's just called concentration. Now the difference is going to be the way you calculate the concentration. Now it's the ratio between mass and volume. The units for mass and volume are going to be dictated by the units that concentration is being represented. Okay, so concentration will always tell you how much of the substance is dissolved in a unit of volume. That's the meaning of concentration. Okay, now let's talk a little bit about dilutions. So let's start here uh, and let's go to the lab. Let's get a beaker and let's prepare a solution. Okay, to prepare a solution, you toss in your solid and add an amount of solvent to get to your expected concentration. So let's call this first solution our initial solution. This initial solution has a molar concentration that I'm calling Ca and has a volume that I'm going to call Va. And also there is an amount of compound that I'm going to call N. From this solution, you can add more water or more solvent, and the result is going to be an increase in the volume. Okay. Now I have the same amount of sample, however, in a larger volume. That's called dilution because the concentration is going to be decreased. And at this point, I'm going to call it final solution. And the final solution has a concentration Cb, a different volume that I'm calling Vb, and the amount of compound that I'm going to call N. Every time you dilute, you start from a small volume and go to a larger volume. What's the result of a dilution? The concentration is going to be decreased because I have the same amount of sample, but now in a larger volume. Okay. Note that in this process, I did not add or removed any amount of compound. Therefore, the number of moles before the dilution is the same as the number of moles after the dilution. Okay, that's the common thing that these two solutions have. Now what I'm going to do is to write number of moles as a function of the concentration and volume, and let's see what we can do here. We know that molar concentration is the ratio between number of moles over volume. To isolate the number of moles, I'm going to move volume to the other side. and that's going to multiply concentration, and we will end up with number of moles is equals to concentration times volume. Okay. We know that the number of moles of the initial solution is the same as the number of moles of the final solution. I'm now going to replace number of moles by concentration times volume. Therefore, I will end up with concentration of the initial solution times the volume of the initial solution has to be equals to the concentration of the final solution times the volume of the final solution. So every time we dilute a solution, this equality here has to be respected. Okay? So that allows you to calculate the final concentration if you have the initial concentration, the initial volume, and the final volume. Or anything in this equation if you have the other three counterparts. Okay? Every time you do a dilution, the equality has to be respected because there is no change in the number of moles. Okay. So to this point, I showed you how to calculate the concentration, and I told you that we can have two different kinds of concentration. First one is called molar concentration or molarity, and it's the ratio between number of moles over volume. And the second one is just called concentration, and is the ratio between the mass and volume. Concentration expresses the amount of substance in a determined volume of solution. And every time we dilute a solution, we have CAVA equals to CBVB because there is no addition or removal of substance. Okay, so the number of moles is constant. So now let's move on and start working in chemical reactions in solution. So we are done with this. And, okay, so let me move on to my desktop. All right, so let's start to work on acid-base reactions. So on chapter number 2, I showed you that compounds can be divided in two different classes, ionic or covalent. Covalent compounds are basically oxides, acids, or molecular compounds, and ionic compounds are salts, oxides as well, and bases. Okay, so right now we will focus on acids and bases. Remember, Ionic compounds are formed by ions or charged elements, and covalent compounds are just formed by elements without charges. Okay, covalency means sharing of electrons, and ionicity means donating and receiving electrons. Quick recap here about acids. We can have two different classes of acids. First one is called hydracids, and it's HX. The name of hydracids is always hydro, name of the parent element followed by IC, space acid. And the second class is called oxoacids. Now the formula is HXO, okay? And nomenclature, name of the parent oxoanion followed by IC, space acid. To remember the name of the most common parent oxoanions, just follow the Nick the Camel, and that will give you the name for the most common ones, okay? Attention here, the nomenclature, guys, unfortunately, you have to know it. It has to be on top, in the top of your head. If you don't remember this, I would strongly recommend you to go back and practice a little more, because if you don't know this, this will get you in trouble for this chapter. Ellen, you have a question?
Yeah, so I just finished doing the chapter 2, part 2 assignment, and at the very end, it had some questions about some compounds that ended in ate, like ATE. But we
Yes.
didn't go over those. Are those in the book?
Yes, the we did go over, that's called polyatomic ions or
Okay.
anions. So that would be PO4 3 minus, SO4 2 minus. So that comes on phosphate, sulfate, and those are the ones that should be there. Okay,
Okay.
and they come from here. So the oxo anion will give you the polyatomic ions.
Oh, okay. Thank
Okay.
you.
Yes, no problem. Yes, so go back and revise this part and make sure you know it. Okay, so quick recap here from acids. So now let's move on to the new compound, the base. Okay, bases. All right, let me switch back to a screen that I can write. All right, bases is the last class of compounds that we will talk about in Chem 109. Very simple compound. General formula is always a metal bonded with OH ions. Bases are ionic compounds always composed by a metal, okay, with a positive charge plus OH minus ions that are called hydroxyl. Nomenclature, pretty simple. The first word is always the name of the first element in the formula, and second word is hydroxide, and that's it. Do not use the prefixes mono, di, tri, etc. to indicate the amounts. It's not needed for bases. So let me show you 3 examples here and how to name them. First example, NaOH. So remember that Na is a metal, and sodium always has a positive charge because it belongs to the group number 1. And in this compound, sodium is bonded to OH that always has a negative charge. Therefore, we have a plus and minus here, which is a characteristic of an ionic compound. How to name this compound? First, look at the first element in the formula, and that's going to be sodium. Because it's bonded to OH minus, that's a base, and to indicate that it is a base, we are going to use the word hydroxide. Okay, therefore, the name for NaOH is sodium hydroxide. Okay, attention here because there is a space between sodium and hydroxide. Okay, so nomenclature here for bases is pretty straightforward. Let's take a look at the second example. The second example is CaOH2. That is the compound formed between calcium. Attention now, because calcium is from the group 2, therefore, the charge is always going to be 2 plus. Calcium is bonded with OH minus. Because there is a 2 plus charge here, we have to have 2 hydroxide ions. And that's the reason for the number 2 right after OH. The parenthesis indicates that we have 2 OH groups bonded to each calcium. Okay. This, of course, is a base because we have OH and a metal. To name the base, first word is the name of the first element. In this case, we have calcium. And the second word is simply hydroxide. All right, and now let's move on to the third and final example. So now I would like to show you a new compound, a new ion. So in the third case, we have NH4OH. So that's a slightly different base. NH4 has a charge 1 plus, and the name for the NH4 cation is ammonium. When ammonium is bonded to OH minus, that means this compound is a base. Name of the base is going to be the name of the first ion here, which is ammonium, followed by the word hydroxide. Okay, so I need you to remember that every time you see the cation NH4 plus, the name for that is ammonium. Okay, do not forget about that. Okay, so I showed you the general formula of bases, showed you that these are ionic compounds and how to name them. When writing the formula of a base, careful with the charges. You need to represent the charges and you need to cross them. Okay. Nomenclature here is pretty simple. first is the name of the first element in the formula, followed by the word hydroxide. Okay, so now let's start to focus our attention to acids and bases, because that's going to be a big part of chapter number 3. Okay. So now let's define acids and bases, starting with acids. So the very general definition of acids is that acid is any sour taste substance. Okay? So for example, here limes are classified as acids because they are sour taste substance. Of course, this definition is not scientific at all. So we need to move on to a more scientific definition. And the most simple one is the definition of Arrhenius. According to Arrhenius, acid is any substance that produces H plus ions in water. Okay, so let's see here an example and how the Arrhenius definition works. So let's start with hydrochloric acid. The formula here is HCl. Hydrochloric acid is a gas at room temperature. And according to Arrhenius, if we dissolve HCl in water, we have to produce H+. We are going to represent the solubilization of HCl in water this way, H2O and the arrow. So that means we are dissolving the compound in water. And every time we dissolve an acid in water, this bond over here is going to break. And we have to produce H+. Now this is dissolved in water. So I'm going to represent that by AQ plus whatever is left. Whatever is left is Cl. If we have a positive here, we have to have a negative for the Cl. And Cl is dissolved in water, so I'm going to represent that by AQ between parentheses. And we know the name for Cl minus. This is called chloride. Okay. So here, that's exactly the definition of Arrhenius acid. Any compound that, when dissolved in water, will produce H plus ions. Okay. Note here that I started from a covalent compound, and in this case, the bond between hydrogen and chlorine is not strong enough, so the water can split that bond, producing ions. The cation is H+, and the anion is chloride. So that was a very simple example and using a hydrocide. So now let's see a second example using oxo acid. Okay. So let's start here with HNO3. So HNO3, that's called nitric acid. Now let's dissolve nitric acid in water. So I'm going to represent that putting water over the arrow. And let's use the Arrhenius definition. So every time we dissolve an acid in water, we are going to break the bond between hydrogen and whatever is left here and produce H plus ions in water. So representing that by the AQ between parentheses, plus whatever was left from the molecule. In this case, we were left with NO3. Attention with the charges. Here we have one positive charge. To balance that, we have to have one negative charge here for the NO3. And this is dissolved in water, so I'm going to represent that by AQ. And we know the name for NO3 minus is Nick the camel, therefore nitrate. Okay. And again, here, I'm just using the Arrhenius definition of an acid. Okay. Every time we dissolve an acid in water, we must produce H plus ions. Careful with the charges. Careful with the charges. And from now on, I want you to write at least this physical state here for the products, okay? I need you to write them. And we can rank different acids as a function of their strength. The strength of an acid is measured by how much H plus is produced. More H plus produced means stronger the acid. Okay? More H plus produced, stronger the acid. In other words, more ions produced, stronger is the acid in solution. Okay, so now let's define bases. Okay, the counterpart here. All right, so let's start with the most simple definition that we can have. Base is any substance that in water is slippery to the touch and also tastes bitter. Of course, this is a bad definition and not scientific at all. One example of bases that I always show here, and students usually don't recognize that, but this is a cashew. Okay, so this is the part that you are used to see, the cashew nut, but cashew has also all this other part here. If you bite it, it's going to taste bitter, sorry, and that's because it's some sort of a basic compound over there. Okay, and the cashew is also very good to make juice. It's pretty tasty, actually. A better definition for bases is the Arrhenius definition. And according to Arrhenius, base is any substance that produces OH minus ions in water. Remember that OH minus is also called hydroxyl ions. Okay, so let's show you two examples here. So let's start with NaOH. NaOH is a solid at room temperature. We just saw that NaOH is called sodium hydroxide. Remember that this is an ionic compound. Charge of sodium is 1 plus. Charge of hydroxyl ions is 1 minus. Now let's dissolve sodium hydroxide in water. I'm going to represent that putting H2O over the arrow, and that means the compound is going to be dissolved in water. Because this is an ionic compound, the water may break the interaction between sodium and hydroxyl, and that's going to split the compound in two parts. The first one is Na plus, dissolved in water, therefore AQ, plus hydroxyl ions, okay, dissolved in water as well, therefore AQ. So OH minus is always called hydroxyl. And here we have what we called an Arrhenius base. Okay, so every time you dissolve a base in water, the bond between hydroxyl and the metal will be broken in most of the cases, and that's going to produce the metal plus and hydroxyl ions. And that satisfies the Arrhenius definition of bases. Okay, let me show you a second example when we have charges that are different from 1 plus. So let's start with calcium hydroxide. Okay, so remember that calcium is from the group 2, therefore has a 2 plus charge, and that's the reason that we have two OH groups in this compound. Okay, name for this guy here is calcium hydroxide. Now let's dissolve calcium hydroxide in water. So let's represent this way, water over the arrow. The water is strong enough to split this compound in two, and that's going to produce calcium. 2 plus, attention here, AQ because now it's dissolved in water, plus hydroxyl ions because this is a base. Dissolved in water, therefore AQ. Attention here now with the charges. We have calcium 2 plus and OH is 1 minus. To balance the charges, we need to have 2 OH minus, okay? So we had 2 here, 2 has to show up in the reagents. Remember that the atoms cannot be created or destructed. Okay? You have to keep the same number of atoms before and after. So be careful when you have CaOH2 when you write the reaction. You cannot forget that you have 2 hydroxyl ions. The strength of a base is measured by how much OH minus is produced. Therefore, higher the concentration of OH minus, that means stronger is the base. In other words, more ions that the base forms when dissolved in water, stronger is the base.
Professor, I have a question.
Yes.
What's the difference between hydroxyl and hydroxides?
There is no difference. It's just a particular name.
I have a question.
Yes.
When making acidic or basic solutions, do you ever have to account for evaporation of any of the products?
You do not, unless you are using very concentrated solutions. But usually when we work in the lab, the evaporation is so small that it's not going to change dramatically the concentrations. So, no.
Thank you.
Mm-hmm. Okay, I think this is a good point for us to take a break. So let's come back at 11:50. Okay, so now we are at a good point in the course to start to study chemical reactions. Okay, so the first one that I will show you is acid-base reactions. Okay, everything in the universe has opposites. Okay, if we have dark, we need to have light. If we like something, we have to dislike something. So you have to have opposites to build some sort of scale and to neutralize things. In the atom is the same thing. You have to have positive charges and negative charges to balance them out. So always looking at opposites. Chemical substances are also they also follow that. Acids are exactly the opposite of bases. Therefore, they will combine and produce a new substance. Acid-base reactions are also called neutralization reaction. Every time we react an acid with a base, we are going to produce a salt. Sorry, I missed here a T here. Salt plus water. And also here energy. So we will focus from now on in this kind of reactions, in neutralization reactions. There are three different ways to write a neutralization reaction. The first one is called molecular equation. The second one is called overall ionic equation. And the third one is called net ionic equation. So let's see how each of them work separately. And I will start here with an example of acid-base reaction between hydrochloric acid and sodium hydroxide. Remember, hydrochloric acid is HCl. We saw that before. And sodium hydroxide, we have been working a lot with this compound today. Oops. And the formula for that is NaOH. Okay? We'll repeat again. You have to know the nomenclature. Okay? If you don't, go back and make sure you are up to speed on nomenclature of acids, bases, and salts as well. Okay, so now let's react HCl, an acid, with sodium hydroxide, a base. Therefore, this is an acid-base reaction, and the products are going to be salt and water. When you are using the molecular equation, you are going to simply combine sodium with chloride. Therefore, that's going to form NaCl, and hydrogen with OH, that's going to produce water. Remember that we always have positive followed by negative. That's why it's sodium followed by chloride and not the other way around. Acid-base reactions are basically a double displacement type of reaction, and we are always going to form salt and water. Okay? Sodium combining with chloride and hydrogen combining with hydroxyl. And that's how you write the molecular equation. Now let's take a look how we will write the overall ionic equation. For the overall ionic equation, there is a trick. The first thing we are going to do is to dissolve the compounds in water. Let's start here with HCl. every time we dissolve HCl in water, we are going to produce H plus AQ and Cl minus AQ. And we are going to do the same thing for sodium hydroxide. Let's dissolve this compound in water. That's going to form Na plus AQ and hydroxyl AQ as well. And now we will react all the ions here. So in this case, sodium plus is going to combine with chloride minus, and H plus is going to combine with OH minus, and that forms water. So this equation over here is called overall ionic equation. In the overall ionic equation, I have to represent the ions reacting and forming the products. Okay. Okay. From the overall ionic equation, we can get the net ionic equation. So let me show you how to do that. I'm going to rewrite the overall ionic equation here. H plus reacting with, plus Cl minus reacting with sodium plus and OH minus, and that's going to form Na plus AQ, Cl minus AQ, and water. All right. For the net ionic equation, we are going to treat this chemical reaction as a mathematical equation, which means any compound that shows up in the reagents and the products will disappear for the net ionic equation. Let's start with Cl minus. Cl minus appears as the reagent and the product, therefore is going to be canceled. And sodium plus also appears as the reagent and the product, therefore is going to be canceled. Therefore, the net ionic equation for this process is going to be H plus AQ plus OH minus AQ, forming water. And that's how you get the net ionic equation. Okay, so now let's add one little detail here for the acid-base reactions or neutralization reactions. So if you look here, I'm representing here in the products Na plus Cl minus dissolved in water. How do I know that they are dissolved in water and not that a solid is formed? Okay, so I need to know if this salt is soluble in water or not. At this point, there is a competition between the interaction cation and anion and the interaction between cation and water and anion in water. Remember, any chemical system will move towards a low energy state or a more stable state. If a more stable state means interaction between ion and water, the system will move towards that. If a more stable state means interaction cation anion, the system will move to that and form a precipitate. To know if a precipitate is formed or not, we have here a solubility table. And remember, a solid will always be formed when the interaction between cation and anion is stronger than the interaction between ions and water. And we have this table here to see when a solid or a precipitate is formed or not. Okay, I don't want you to memorize the table, but I need you to know how to read the table. The first column, we have different ions. Second column tells us if it's soluble or not. And the third column is any exceptions to the rule. Okay, so how to read the table? Let's start in the first line here. Ions from the group 1 will always form a salt that is soluble in water. That's what the table says. Ions from the group 1 will always form a salt that is soluble in water. No exceptions to this rule. If we move all the way here to phosphate, phosphate will always form insoluble salts, except when it combines with group 1 or ammonium. Okay, so that's what the table is telling you. All right, so what is a precipitate? Precipitate is any solid in solution. So let's assume here we have solution A, and we are going to mix the solution A with a solution B. If this reaction produces a salt that is not soluble in water, you're going to see here the formation of a solid at the bottom, and that's called precipitate. And the rest is called solution. Okay, thank you for the question. Okay, so now let's use the knowledge here from the table to write chemical reactions. Precipitates may be formed during an acid-base reaction or a salt-salt reaction. Let's start with acid-base reactions forming precipitates or insoluble salts. Okay, the first example here that I would like to show you is the reaction between hydrofluoric acid and calcium hydroxide. Hydrofluoric acid is HF. Calcium hydroxide, we looked at that earlier, and it's CaOH2. Okay, attention here with the formulas. So let's write first the molecular equation for this reaction. Molecular equation is pretty simple. HF plus CaOH2. So that's an acid-base reaction. So we know that we have to form water and a salt. Calcium is positive. That's going to combine with fluoride, forming CaF. Attention here with the charges. Calcium is always 2+, and fluoride is always 1-. We need to cross the charges here. So that's going to form CaF2, attention. That's our salt plus water. Okay, this is liquid. Now that we know what was the salt that was formed, we go back to the table and let's take a look. Is this salt soluble in water or not? So let's go back here to the table. So here we have fluoride. If we go back to the table, fluoride is right here, the last one. Fluoride always forms insoluble salts. The exception here is when combined with group 1 or ammonium. In this compound, fluoride is combined with the group 2, therefore it will form a solid. And I'm going to represent that using the parentheses and S. You can always represent the formation of a solid by an arrow pointing down. Okay, so visually it means when we have HF and we mix with calcium hydroxide, the result will be the formation of a solid that we know the solid is calcium fluoride, and you will have water. And the solid here we can call precipitate or simply PPT. And that's how you read the table and use the table, okay? Every time, pay attention, every time you form a precipitate, that means the interaction between cation and anion will not be broken by the water. Let's see what's the effect of the formation of a precipitate in the overall and net ionic equations. So now let's write the overall ionic equation for this process here. Remember that the trick is always dissolve the acid and base in water first. HF dissolved in water is going to produce H plus and F minus. Calcium hydroxide dissolved in water, that's going to produce calcium 2 plus AQ and OH minus. Attention here, if we have A2, we need to have A2 here. Do not forget about that. Now let's, yes.
Sorry, I have a question. I don't mean to interrupt. I can ask it later if.
Let me just finish this one.
Okay.
Okay. So now let's react all the ions. Positive will combine with negative, and the same thing here. That's going to form calcium fluoride, solid, plus water. Okay. So now attention, because when you have the formation of a solid, you are not going to write calcium 2 plus fluoride, okay? You have to write calcium fluoride and then water. Obviously, this reaction is unbalanced, so we need to take care of that. We have 2 fluorides on one side. Let's add a 2 here, and a 2 here, and 1 and 1. And that takes care of the balancing. Okay, so attention. When there is a formation of a solid, you have to write the formula of the salt. If the salt is soluble, then you write as ions. Katie, go ahead.
Sorry, my question was about balancing, but you answered.
Oh, there you go.
For
Yes.
interrupting.
No problem. And obviously, the molecular equation here, sorry, is not balanced. So let's balance this. And 2, 2, 1, and 1 here as well. Okay, so now let's take a look at the net ionic equation. For the net ionic equation, the trick is to first write the overall ionic equation. So let's repeat what we have here. Oops. And it's going to produce calcium fluoride, solid, and water. Okay, so let's take a look at the net ionic. Okay, for the net ionic equation, we are going to treat the chemical reaction as a mathematical equation. That means everything that shows up before the arrow and shows up after the arrow can be canceled, okay? Treat it as a mathematical equation. So let's start with H plus. H plus shows up in the reagent side, but does not show up in the product side, therefore cannot be canceled. Let's keep it to H plus. Now let's take a look at fluoride. F minus shows up in the reagent side, but does not show up in the product side. Okay, we have to have exactly the same thing. If it doesn't show up on both sides, we need to keep it. The same thing for calcium. Only appears on the reagent side, and the same thing for the hydroxyl. None can be canceled in this case because we have the formation of a solid or a precipitate. And I'm just going to repeat whatever was formed for the products. Okay? So when we have the formation of a solid, the overall ionic equation is going to be identical to the net ionic equation. All right, so the trick here is to pay attention to the formula of the compounds, pay attention to the balancing, and check if a precipitate is going to be formed or not. So that will have a heavy influence to the overall and ionic equations. And at this point, I want you to write the physical states, at least for the products, okay? If you follow these steps and be careful with charges, there is no secret here writing neutralization reactions. Okay, I want to show you a second example and then we will finish for today. So now let's react a salt with a salt. The first one is lead nitrate, and this one you don't need to know the formula, but it's going to be PbNO3 reacting with sodium iodide, NaI. Starting with the molecular equation, PbNO3 reacting with sodium iodide, that's going to produce two salts, okay? So this is a double exchange reaction. Always the first one is going to combine with the second one here, and the first one here with the second one over there. That's going to form Pbi. In this case, lead is 2 plus, so therefore there is an 2 over there, and sodium will combine with nitrate. We need to balance the reaction. There needs to be a 2 here, and a 2 here, 1 and 1. Okay, so now we have two salts. The first one is lead iodide, and the second one is sodium nitrate. Let's go back to the table and let's check if one of those are insoluble or if both are insoluble. The first one is iodide combined with lead. So that's right over here in the fourth row. We have iodide here. Iodide forms soluble salts, except when combined with silver, lead, or mercury. Therefore, we know that lead iodide is going to be a solid. Now let's check for sodium nitrate. Sodium nitrate is a salt that contains a group 1 cation. Therefore, they are always soluble. They will never form precipitate, okay? So they stay dissolved in water. And this is a very classic reaction. Lead iodide is this very beautiful yellow precipitate formed here in the reaction, okay? So very characteristic. Okay, With that being said, on Thursday, I will show you the overall ionic equation and the net ionic equation for this process. Okay, I will see some of you later today and the other half tomorrow morning. Okay, have a good rest of your day.
Thank you, Professor.
I had a question.
Yes.
Done. Sorry, we have a home phone.
No, go ahead.
When will you be uploading these notes? 'Cause I kind of
The
missed.
notes for this class or the?
Yeah, the ones we just took right now.
I will try to do my best to do right now.
Okay, thank you.
Okay.
I just missed some of it, so.
No problem. No problem.
Okay, thank you. Bye-bye.
Mhm.
Thank you.
Bye-bye.